academic penalty, which is not a good thing. So keep that in mind. All right, do we have any questions? We're in the chapter talking about gases and the gas laws, and we've outlined the beginning and said that people were able to do this around the 1600s or so because they had the equipment and the logic of scientific investigation was coming into play around that time. And one of the guys that did one of the first investigations with gases is a guy by the name of Robert Boyle. And so what Boyle decided or discovered was that if he put gases into a movable piston, like so, he had a gas in a container, and the gas in the container was present with a certain volume, so we'll call it volume 1. And the pressure out here was a certain volume, certain pressure, we'll call that P1, indicating that the piston is pushing down on these gases, and it reaches some point where it stays steady. Then what he decided to do was to push down on the piston, increase the pressure, maybe pile some weights on there or use his hand or whatever, and he found that if he doubled the pressure, then the volume was cut in half. So he ended up with a new pressure and a new volume. What his result meant was that the volume was directly proportional, so we use a proportionality constant of K, to 1 over the pressure. In other words, they're what we call inversely related. As one gets larger, the other one gets smaller. So as the pressure got larger, the volume got smaller, and vice versa. And so this is what we know as Boyle's law. Now we can rearrange this into a volume times a pressure is equal to a constant. And that's important, that we equal a constant value. Because what it means is that in our first experiment, P1 times V1 is equal to a constant, K. In the second experiment, when we have changed the pressure and consequently changed the volume, P2 times V2 should equal the same K. As long as we have the same amount of gas and the same temperature, we're keeping all other parameters equal, then these two values should equal the same constant. And if that's true, then it means they're equal to each other. So P1 V1 equals P2 V2 is a popular form of what's called Boyle's law, showing the relationship between the pressure and the volume for two different instances. Now sometimes we like to see this stuff work and see it happen. And I have a little device here that can do that. This is what's known as a potato gun, although we're not going to use potatoes. It's a piece of copper tubing. There's nothing in the tubing. It's just a hollow piece of copper tubing. And then there's this dowel rod that has a little piece of rubber on the end so that it fits rather snugly into the tube so that air doesn't rush around it. And what you can see I'm going to be doing is, right now there's a certain volume in the tube. If I were to push this rod in, what am I doing? I'm changing the volume. I'm changing the volume because now if it's here, then the effective gas is only in this much of the tube. And if I push it all the way in, then the amount of gas is only in this part of the tube here. Now, if I'm changing the volume, if this were a closed system, then I would also be changing the pressure. And if the volume is getting less, the pressure should be getting more. If the pressure becomes great enough, I should be able to shoot a rubber stopper out into the crowd. So, let's give this a shot.
Wow.
Don't shy away, dude. All right, here we go. Give it a try. I'm going to push the dowel rod up and kill the student. Try it again?
Yeah.
Now you know what's going to happen. Oh, yeah. I will change directions.
Oh, God.
Let me get a little more volume back here. You willing to play? Let's try it.
We need protective goggles. I know.
She's not expecting me.
All right. Gonna push the rod up. Good job. We'll count that as a catch. All right. So Boyle's law in action. As we decrease the volume, we increase that pressure. The pressure became great enough to pop the cork out the end of the container. So let's try a problem that we might encounter with this relationship. So suppose that the pressure of 10 liters of gas at 740 is 740 torr at 0 degrees centigrade, and we reduce it to 700 torr at 0 degrees centigrade. We want to know what is the new volume. So as soon as we have a problem like this, we evaluate what parameters are we dealing with. The temperature is staying constant. The amount of gas is sort of implied to stay constant. We have 10 liters, so we have a volume and we have a pressure, and we're going to a new pressure. So that just screams of Boyle's law. So we would start with P1, V1 is equal to P2, V2. Now what I'm doing is I'm looking for a new volume. So I'm looking for one of the volumes. It doesn't matter which volume I look for. Okay, I can look for either V1 or V2. I can call it V1 or V2. But I have to make sure that the other volume and its pressure are linked together. In other words, I don't have freedom of choice totally here. Maybe the best thing to do is to create a little table somewhere on your scratch paper or in the margin of the problem and say, let me label these terms to see what it is that I'm actually solving for. So, pressure of 10 liters of gas. So 10 liters of gas, is that a volume or a pressure?
Volume.
So will I call it V1 or V2?
Volume.
It doesn't really matter. So it's the first one I came to, so I'm just going to call it V1. Pressure is 740 torr. Is that a pressure or volume? Pressure. P1 or P2?
P1.
Doesn't matter.
Yes.
Yeah, now it matters greatly that we have that as P1 since we labeled the 10 liters as V1. And we're going to reduce it to 700 torr. So that's a pressure, and it's a change, so that must be P2. So 700 torr. And so it's obvious now that what I'm looking for is V2. Good news, I'm asked to find the new volume, and so V2 is a logical variable to be solving for. So I come back to my equation here, and I say, let me solve this for V2. So V2 must be equal to P1 V1 over P2. Now all I have to do is take my numbers from my little table here and enter them into the problem. P1, 740 torr. V1 is 10 liters. And P2 is 700 torr. Now the only condition we have to place on here is the units aren't that critical. In a later relationship that we develop, the units are going to be very critical. But in this case, they're not that critical. But what has to be true about the two pressures? They have to be in the same unit. Whether that unit be something we call an atmosphere, or whether it be something we call a torr, or a millimeter of mercury, whatever, it just has to be the same as each other. Otherwise, we don't get cancellation and we'd have to make a conversion. In this case, you can see what's going to happen. The torrs are going to cancel. I'm going to be left with an answer that's a liter, and that's a volume, so that's good. That's what I'm looking for. And even here, the volume unit is not critical. If this were milliliters, would this still work?
Yes.
Yeah, it's just that my answer would be in
Milliliters.
milliliters rather than liters. So I can carry out this problem, and I think if my math is right, I get 10.6 liters. You can check. You did? Okay. So we're good. Now, when Boyle did his experiments, he carried them out with a constant amount of gas. He was able to do that, and that's what this depends upon, that the amount of gas be fixed. Because you can imagine what would happen here in this tube, for example. The pressure increased because I decreased the volume, right? Well, why doesn't the pressure increase when I do it now? Because it's an open system, and so what's that doing? It's just pushing the gas out. And so I'm doing an experiment that does not have a fixed amount of gas, and so it's not going to work in this relationship. So this relationship depends upon there being a fixed amount of gas that stays constant throughout the experiment. The other thing that happened was he didn't give any thought at all to temperature. Didn't cross his mind, but he performed all of his experiments at room temperature. And so effectively the temperature was held constant. And that was a good thing because we find out that there's a connection to temperature. Yes, sir.
So what if you had closed that, and you still had like the rod in there, and if you were somehow able to open it up, would that make it a vacuum inside?
Yeah. Can I have my stopper back? You touch that. Let's suppose we do what you suggest. I've got the small volume, and now I'm going to put the rubber stopper in here, okay? And then I'm going to pull the rod back. All right, so what's happening now? It's actually forming a lower pressure inside, as we would expect, larger volume, lower pressure. And so what happens? You can see that the rod gets pulled back in. It doesn't really get sucked back in. Science never sucks. What's happening is that we're lowering the pressure on that side, but the pressure out here stays the same, and so it's pushing it back in. Now, why doesn't it push it all the way back in? This is not a perfect system. Some of the gas is escaping around the edges of my little stopper plug that's on the end of this dowel rod, and so I'm actually changing the amount of gas at one point during the course of this experiment. But you could actually, if you were to do this, you can actually feel the tug. Maybe after class you can come up and play with it. Pull this out, you can actually feel the tug of going back in because of that decrease in pressure that's happening inside the tube. Maybe I'll keep it loaded here in case somebody shuts their mouth off. See what happens. Okay, so it was 100 years later that a Frenchman, a guy by the name of Jacques Charles, decided to measure the effects of temperature on the volume of a fixed amount of gas. And he found that there was a relationship between the two. Charles found that a gas at 0 degrees centigrade expanded about 1/273rd of its volume for every degree in centigrade change that took place. Or what he did was actually plot a value of volume versus temperature, and he got a line that looked something like this. Now, you are actually going to do this experiment in the laboratory. It's your last lab, so I suspect you haven't gotten there yet. But toward the end of the semester, you are going to take a flask of air, gas, and you're going to heat it up, and then you're going to cap it off with your finger over the opening so that gas can't escape, and you're going to put it into different beakers that hold different temperatures of water. So you're going to do ice water, you're going to do a medium warm water, you're going to do a room temperature water, and you're going to have the value for boiling water because of the way you start the experiment. And so you're going to have 4 points that you actually plot on this kind of a graph to establish this line. Now what he found was that if he extrapolated his graph, and the reason we have to extrapolate is what happens as we get to colder temperatures. Eventually the gas will do what?
Stop.
Slow down, condense.
It'll condense. It'll go into a liquid form. And if it's in a liquid form, it's no longer acting like a gas. Does that make sense? And so at some point, all gases are going to liquefy. And so in order to see where this ends up, we have to extrapolate. We have to go down. And what he found was that if his temperature was measured in centigrade, that this hit the axis at negative 273 degrees centigrade. So what he found was that the volume was related to the temperature. So the volume related to the temperature by the equation of a line. So remember that the equation of a line is y is equal to mx plus b. So y is my volume, x is my temperature here. So I'm doing that. But when the volume was 0, we found that the temperature was negative 273. So actually, we could rewrite this as that the volume is equal to some constant k, which is the slope, times the temperature plus 273. And so it was decided at that point, based upon this relationship, that it would be kind of neat to have a temperature scale that got rid of that plus term in the temperature. And so we established what was called the Kelvin scale. And the Kelvin scale, Kelvin temperatures, are simply the centigrade temperature plus 273. Now I think it's actually 273.15, but we rarely use that full value. We generally stick with 273. It's easier to remember, easier to work with. So for most practical purposes, it does the trick. Okay? And so our relationship is that the volume is equal to a constant times capital T, which we indicate is the temperature in Kelvin, degrees Kelvin. The interesting thing about the Kelvin scale is that since you can't have a gas that has a negative volume, could we actually go to a lower temperature than this? No, we shouldn't be able to. And so this is what's called absolute zero. When the Kelvin temperature is 0, which is negative 273 degrees Celsius, the gas should technically or theoretically have 0 volume. And that should theoretically then be the lowest possible temperature we could get to. And it's true. It's called absolute zero. It's the point where all energy is released from the sample. It has no more energy to lose, and so the temperature can't drop any further. So it's the lower limit on the temperature scale. Now, what this means for us is that in all of our relationships that we develop for gases, if temperature is in there, we have to use Kelvin. But in many cases, the problem will give you the temperature in centigrade. So you have to get very used to saying, oh, if it's a gas-law relationship, I need to change the centigrade temperature into Kelvin, sort of automatically. Otherwise, the relationship that you're developing won't work. So let's try a couple of these. About 25 degrees centigrade. Tell me what it is in Kelvin. 100 degrees centigrade. Tell me what it is in Kelvin. 223 Kelvin. Tell me what it is in centigrade. Go, you have 12 seconds. Time is up. First one, 298, 373,
-50.
-50. We agree? Joe, I think you've got it. All right, so this law, this relationship was named after the guy that came upon it, and that was Jacques Charles, and so it's known as Charles' Law. And Charles' Law simply says that the volume of a given amount of gas varies directly with the temperature if the pressure remains constant. We always have to have the constant value for those other parameters when we're looking at what happens to one with respect to just one other parameter. So we're looking at what happens to the volume when we change the temperature. We've got to keep the amount of gas and the pressure constant in that relationship. Otherwise, we're observing two effects at the same time. So the result of our experiments, or his experiments rather, I've erased it, is that the volume over the temperature is equal to a constant. Now, if we say, okay, let's run this experiment in two different conditions, then the volume's going to change, the temperature's going to change, but the constants shouldn't change. And so if we change the temperature and measure the new volume, then V2 over T2 should be the relationship. And this is called a direct relationship, because if one increases, the other increases. Remember, in Boyle's law, we called it an indirect relationship. As one increased, the other decreased. And so we saw that. So we could put these together and actually come up with an alternate form of Charles' Law that says that the volume of 1 times the temperature of the second experiment is equal to the volume of the second experiment times the temperature of the first experiment. Now, doing the same type of experiment with temperature but measuring pressure, if the volume was held constant, we also have a pressure relationship here. So we also have that P1 T2 is equal to P2 T1. So the pressure and the temperature are directly related as well. Increase that temperature and you increase the pressure. There's a good example of this, although I'm not going to do it in the demonstration for you. But if you are, why does the instruction on a can of spray paint say to dispose of this, do not put it in the fire? Because as you put it in the fire, that's a closed system. The valve on the top is not open. And the fire is going to heat the contents of that can. And when it heats the contents of the can, we expect the pressure to go up. If the pressure goes up high enough, then just like our little rubber stopper gun here, it's going to explode. And when a can explodes, it's going to take pieces of sharp metal and toss it out at you and can actually cause some physical damage. So just like the rubber stopper hitting the head in the back of the room, cause a little damage. Hopefully not too much brain damage. We'll see. All right, so let's try a problem. So a 5-liter container of gas is cooled from 50 degrees centigrade to minus 20 degrees centigrade. If we keep the pressure constant, what's the new volume? Go, I'll give you 12 seconds. Okay, you should have an answer. Let's see what we would do. Here's our relationship. Here's my little table over on the side. I'm looking for V2, the new volume. What's the one thing I've forgotten to do here?
Convert it to Kelvin.
I've got to make these into Kelvin, so I'm going to do that right away. So 273 is what, 323 Kelvin, and minus 20 is 253 Kelvin. So I'm going to make those as soon as I can so I don't forget to do them later. It's a very common thing, very common student mistake is to not make the change into Kelvin. So I'm looking for V2 here, so V2 should be equal to V1 T2 over T1. Putting in the numbers from my table, I have 5 liters times 253 Kelvin over 323 Kelvin. The Kelvins cancel, and my final answer should be, I get about 3.92 liters.
If you wait to convert it,
I'm sorry?
will you get the same answer?
What do you mean wait to
Wait.
convert?
Like if I would have done, in that equation, instead of converting it to Kelvin first, use the 50 and negative 20 degrees Celsius, calculating my answer, and then converted it to Kelvin, would that be the same?
I'm a little confused. You're saying that you want to put 5 liters and
The negative 20.
negative 20 over the 50
Mm-hmm.
and actually calculate a number there?
Yeah, if you do that, and then what you come up with, you convert to Kelvin, would that throw it all the way off?
But it doesn't make any sense because I have liters here and liters is a volume. So if you convert the liters to Kelvin,
Oh, yeah.
that's not the same thing. And the quick or solid answer to your question is no. You cannot do these relationships. Even if you were saying, well, if I'm looking for a temperature, can I make the change later? And the answer is no. You
Okay.
have to do it in Kelvin.
I know you said something about, so you won't forget to do it later, so you can't do it later.
Right,
Okay,
right.
okay,
What I meant to say is so I don't forget to do it.
okay,
Because if I don't do it and I forget, then I'm going to get the wrong answer.
okay.
It's an order of operations problem because you're just adding to the
Correct.
calculus. So if you do it later, you'll end up with that.
Now you can do it, I mean, I suppose you could put minus 20 plus 273 right into the equation here. But then you have to do that in that order. You have to put that in parentheses and do it in that order to get your right answer. All right.
In all of these, there's been K like a constant. That's not some sort of like value we have to look from the back of the book. It's like it's
Probably not, because what we're going to do is to try to link these together. The K and the K led us to that. And that's the relationship that we want to know. Okay? And this is the relationship we want to know. So the K value itself is immaterial. Although you could easily calculate it. All you have to do is take your volume 1 and T2 and it's going to equal some number.
right.
Okay?
It's-
But there's not much you would do with that. You would put it back in there for the other one, and so it's easier just to do it directly.
The K was more to show us how to get to.
Yes. It was showing you that there was a constant involved in the relationship, and then what we can do is link these together. Now, it's going to be convenient for us to work with what are called a set of standard conditions. And so people that work with gases have made some standard definitions for certain conditions. Standard conditions of temperature and pressure, which is abbreviated STP, standard conditions of temperature and pressure, are defined as 0 degrees centigrade, so that's 273 Kelvin, and 1 atmosphere, which remember is 760 torr or millimeter of mercury. Those two are interchangeable. But these also become the conversion factors for you. So that if you're given the value in torr and you need it in atmospheres, and in a minute you're going to see why we need that, then you have that relationship. But you need to know these standard conditions. So that if somebody comes up to you on the street and says, what are the standard conditions of temperature and pressure for gas law relationships? You will say
0 degrees Celsius.
0 degrees Celsius,
1 atmosphere.
1 atmosphere. without hesitation.
Well, we need to know the 760 torque.
No, I'll give you that. I will give you conversion factor. So I'll give you 760 torr is equal to 1 atmosphere on the front page of the exam. Okay. Now I'll probably forget to put millimeters of mercury, or I might put millimeters of mercury instead of torr. So you should know that those two really mean the same thing. It doesn't matter which one of those we use there, but they're different than atmospheres. Okay. Now, what if we wanted to do two things? What if we had a system, we've made the point that if we're doing Boyle's law, we had to have a constant amount of gas and we had to have a constant temperature. If we're doing Charles' law, we had to have a constant amount of gas and we had to have a constant pressure. What if we want to change up two of those guys? What if we want to change the temperature and the pressure and calculate a new volume? Well, we are able to mathematically combine these two laws into what's called the combined gas law. And the combined gas law looks like this. P1V1 over T1 is equal to P2V2 over T2. And so there's what's called a combined gas law. And it's a mathematical expression in 6 variables. Give me any 5 of those variables and I can solve for the unknown 6th variable. Well, what do you mean? All right, we'll do an example. So a volume of gas is 420 milliliters at 25 degrees centigrade and 740 torr. So define the temperature and the pressure. Find the volume at a new temperature and a new pressure, namely 75 degrees centigrade and 1.20 atmospheres. So this is perfect for the combined gas law. Again, my approach would be to set up a little table somewhere on your scratch paper or in the margin. P1, V1, T1, P2, V2, T2, and label things accordingly. So I have 420, that's a volume. So I'm going to put that in here, keeping my units. 25 degrees centigrade is the first temperature. So 25 degrees centigrade, that's a 298 Kelvin. 740 torr is my first pressure, so 740 torr. And then find the volume, so I must be looking for V2 at 75 degrees centigrade. There's my T2, 75 degrees centigrade, and that would be 248 Kelvin, another 50 on there. And then P2 is 1.20 atmosphere. So here I see a case where my pressures don't agree with each other. So what am I forced to do? I need to make a change. I need to make a conversion. And I can do either one. I can convert this torr to atmospheres, or I can convert this atmospheres to torr. Since I'm here, I'll just take that there are 760 torr in 1 atmosphere. And so 760. 902?
912.
Of course, 912. Sure. So I have some flexibility on the pressure, but I have no flexibility on the temperature. That's got to be in Kelvin. Yes, ma'am.
Shouldn't T2 be 348 Kelvin?
How much?
348 Kelvin.
Yes, it should. Did that on purpose, to see if anybody catch it. We have one observant student in the class. You get the gold star for today. Excellent. It's 3:48. That's the problem you have when you start using your head instead of your calculator. So. Wise idea. All right. So what am I looking for? V2. Can I solve this expression for V2? It's P1 V1 T2 over T1 P2. And then just go to my table and plug in these numbers. P1, 740 torr. V1, 420 milliliters. T2, jumping down, 348 Kelvin. T1, 298 Kelvin. And P2, 912 torr. And notice that I'm using my units. We instructors are pretty adamant about you always using your units because it really helps you prevent mistakes. It keeps you from making mistakes when you're doing these types of calculations. The torrs cancel, the k's cancel. I'm going to be left with a value in milliliters. And that's okay, I'm looking for a volume. And so I do the math here and I end up with 398 milliliters. Does my answer make sense? That's always a good thing to ask. What am I doing to the pressures? I'm increasing the pressure. If I'm increasing the pressure, what should happen to my volume? Should get less. And what am I doing temperature-wise? I'm increasing the temperature, so the volume should get more, so now I'm at an impasse. Is it going to get more? Is it going to get less? It's going to depend upon which one has the greater bite in the system. So 398, good guess as any. Put my faith in the math at this point. All right, questions? Yes?
So units for volume and temperature, or volume and pressure don't matter as long as they match, but temperature has to be in Kelvin.
In this relationship, that's true. Yeah, the temperature has to be in Kelvin, no question about it. The other guys, you have some flexibility as long as they're the same. Yeah. So there's another relationship. A guy by the name of Guy Lussac did some investigation with gases. Let's take a look at what he did. And he got some puzzling results. He was looking at the reaction of gases in terms of their volumes. And the results that he got didn't make sense to him. And so we needed somebody to come along and make some sense out of it, make some explanation. So what's happening here? We are revving up the projector to take a look at his experiments and his experimental results. Good luck. Look. It's there. So let's look at his first experiment. Seemed very logical to him. He took a volume of hydrogen. So this square represents a fixed volume. If you want to think of it as 1 liter, that's fine. If you want to think of it as 10 liters, that's fine, as long as the squares are the same. So he took a fixed volume of hydrogen, reacted it with a fixed volume of chlorine, and lo and behold, got twice the volume. That's exactly what he was expecting to have happen. And if you think about it, you take this much and this much put together, you get the sum of the two. But then he tried it with hydrogen and oxygen and got quite a different result that was confusing to him. He took 2 volumes of hydrogen, 1 volume of oxygen, put them together, they reacted, and instead of making 3 volumes of the product, it made only 2 volumes of the product, 2 waters. And so this really blew their minds. How could this happen? The first one, very logical, very straightforward, expecting the same thing to happen for the second example, not the case. And then he tried a third example, got even worse. 1 volume of nitrogen. He took 3 volumes of hydrogen, put them together, and they made 2 volumes of the product instead of the expected 4 volumes of the product. So he kind of discovered that gases react in small whole number ratios with each other, but not in the expected ratios that you would think should happen when you're putting these volumes of gases together. The problem was solved by a young scientist named Amedeo Avogadro. And what Avogadro said was it was a totally new revolutionary idea. He said that elements could exist as molecules that had 2 or 3 atoms glued together. Before his time, nobody thought in those terms. An element was simply an element, a fixed number of particles. Dalton, the father of the atomic theory, said what? Hydrogen was hydrogen. Oxygen was oxygen. Oxygen was fatter than hydrogen. We knew that the masses were different, but that's what he thought. And so his conclusion was that when you combine these together and make water, water should be HO. Dalton went to his grave thinking water should be HO instead of H2O. But a young guy by the name of Avogadro came forward and said, look, I think that equal volumes of all gases at the same temperature and pressure contain the same number of particles, same number of molecules or atoms, depending upon what kind of substance we are talking about. And so the picture we have for that is there's equal volumes here. But clearly those gases are different sizes. But notice that each volume, if we have the same conditions of temperature and pressure, each volume contained the same amount of gas. It didn't matter what gas you were dealing with. That equal volumes of all gases contained equal numbers of molecules. He had some pretty good argument for this. He said, look, I can take a box of hydrogen, a volume of hydrogen, and I can spark it. So he put a little energy in there. And what happened was, to keep the conditions of temperature and pressure the same, he had twice the volume. Now, according to everyone's belief system at that time, that should not happen. If you've got a volume of hydrogen, and hydrogen is just an atom, what did Dalton say about atoms to begin with? Anybody remember? They were indestructible and indivisible. So how can this possibly be the case? If they're indestructible and indivisible, what's going on to make these become 2 volumes? What Amedeo Avogadro said was that hydrogen actually existed as a molecule, an H2. And what the energy is doing is it's breaking the chemical bond between the 2 hydrogens and producing hydrogen and hydrogen. Now, in the reaction here, notice that for every 1 molecule, you are going to get 2 of the atoms. And if the conditions of temperature and pressure are going to be the same, then, according to his hypothesis that all volumes have the same number of particles, you're going to have twice the volume to do this. Nobody believed him. He died, I think around the age of 50, 52 or whatever, and nobody believed him. It was after his death that they realized, oh my God, Avogadro was right. And now he's famous, and we have a number named after him called Avogadro's number, which is 6.02 times 10 to the 23rd, which kind of honors him in the long run here. So what does this mean? Well, Avogadro's law is actually telling us is that the volume is equal to some constant times the number of gaseous particles. The number of gaseous particles we'll designate as N here. So, we've developed 3 laws at this point. Let me summarize them very quickly for you. We have Boyle's law, which says that the volume is equal to a constant, let's call it K1, times 1 over the pressure, that the pressure and the volume are inversely related. We have Charles' law, which says that the volume is equal to K2 times the absolute temperature. Remember, that's got to be in Kelvin. And we have Avogadro's law, which says that the volume is equal to K3 times the number of particles. What we will do on Monday is to combine these laws together into one cute, simple little package that is a very powerful tool for us. And it's called the ideal gas law. So we'll do that on Monday, put these things together, and then work some ideal gas law problems. We also have to start thinking about an exam. Take a look at your schedules. Maybe on Monday we'll try to vote for a day when we can have an exam coming up in the future.